Welcome! Today, we'll be tackling LeetCode problem number 2086, minimum number of buckets required to collect rainwater from houses. This is an interesting problem that challenges us to optimize placement strategies for collecting rainwater while adhering to certain constraints. Let's dive in and explore the solution together. In this problem, we are tasked with determining the minimum number of buckets needed to collect rainwater from all the houses on a street. The street is represented as a zero-index string called street, where each character can either be an H, representing a house, or a dot, representing an empty space. To collect rainwater, we can place a bucket in an empty space adjacent to a house. This means a bucket can serve either the house directly to its left or its right, but not both at the same time. Additionally, a bucket cannot be placed on a house itself. The objective is to calculate the smallest number of buckets required to serve all the houses, or determine if it's impossible to do so. If it's impossible, we return -1. The input consists of the string street, which has a length in between 1 and 100,000, and the output is a single integer representing the minimum buckets or -1 for an impossible case. Let's consider an example to clarify the problem. Suppose the input is street equals HH. Here, we have two houses at indices 0 and 3, with empty spaces in between. To ensure both houses are served, we can place a bucket in the empty space at index 1 to serve the first house, and another bucket in the empty space at index 3 to serve the second house. This arrangement ensures that every house is served with the minimum number of buckets, which in this case is 2. On the other hand, consider the input street equals H.H. In this scenario, a house at index 1 has no adjacent empty space where we can place a bucket. Consequently, it is impossible to serve all the houses, so the output is -1. Now, let's look at another example. If the input is street equals .hh, the solution is to place a single bucket in the empty space at index 2. This bucket will serve both the house at index 1 and the house at index 3, as it is adjacent to both. This efficient placement minimizes the bucket count to 1, which is our final output. Moving on, the constraints of the problem remind us that the length of street can be as large as 100,000, and every character in the string will always be either H or dot. This means our solution needs to be efficient and capable of handling very large inputs while adhering to the rules of adjacency and exclusivity for bucket placement. Finally, let's discuss some important edge cases. If the street contains no houses, such as street equals, then no buckets are needed, so the output is 0. Conversely, if the street has houses but no empty spaces, like street equals HHH, it's impossible to place buckets, and the output is -1. For a single house with no adjacent empty spaces, such as street equals H, the output is also -1. If all houses are directly adjacent, like street equals HHHH, no bucket placement is possible, resulting in -1. However, in a case where houses alternate with empty spaces, like street equals HHH, we can place one bucket per empty space, resulting in an output of 3. To solve this problem efficiently, we use a greedy approach, iterating through the string and placing buckets in a way that minimizes their count while ensuring every house is served. If at any point a house cannot be served, we return -1 immediately. To solve this problem, we need to determine the minimum number of buckets required to ensure every house in the street has one nearby to collect rainwater. The key constraint is that buckets can only be placed in empty spaces adjacent to houses. If it's not possible to cover all houses, the result should be -1. One approach to this problem is the brute force method, which involves trying all possible bucket placements in the empty spaces and checking if every house can be covered. For each configuration, we confirm that every house has a bucket either to its left or right. If we find a valid arrangement, we record the number of buckets used and aim to minimize it. However, the brute force solution is computationally expensive because the number of combinations grows exponentially with the number of empty spaces. This makes it impractical for larger inputs, as the time complexity is 2 to the power of m, where m is the number of empty spaces in the street. A more efficient way to approach this problem is by using a greedy strategy that focuses on placing buckets optimally as we traverse the street. In this method, we examine each house from left to right and place a bucket in the earliest valid spot to ensure coverage. Ideally, we place a bucket in the empty space immediately to the left of the house, as this placement can potentially cover both the current house and a previous one. If the left position isn't available, we place the bucket in the empty space to the right of the house. If neither position is valid, it becomes impossible to cover that house, and we return -1. The greedy approach ensures that we avoid redundant placements and overlaps by prioritizing efficient coverage. This method is highly efficient, with a time complexity of O(n), as we process each house in a single pass and make constant time decisions for bucket placement based on the local conditions. An alternative to the greedy approach is a two-pass solution, where the first pass marks potential bucket positions without placing them, and the second pass validates these positions to ensure all houses are covered. While effective, this two-pass method is less intuitive and more complex to implement compared to the greedy strategy. Although the two-pass solution achieves the same linear time complexity as the greedy approach, it is less straightforward and requires additional reasoning to ensure correctness. For this problem, the greedy strategy was chosen because it is simple, clear, and efficient. By scanning the street in one pass and placing buckets as early as possible, we minimize the total number of buckets while ensuring all houses are covered. The key insight here is that placing buckets early helps maximize their coverage and reduces the likelihood of redundant placements later. While the brute force approach guarantees correctness, it is computationally infeasible for large inputs. The two-pass strategy, though efficient, adds unnecessary complexity in comparison to the greedy method. Ultimately, the greedy approach strikes the right balance between performance and simplicity, with a final time complexity of O(n) and a space complexity of O(1), as it only requires a single traversal of the input and uses a constant amount of extra space. To start, let's frame the problem. Imagine you have a street represented as a string where H denotes a house and dot represents an empty space. Your task is to figure out the minimum number of buckets needed to collect rainwater from all the houses. A bucket can only be placed on an empty space adjacent to a house. If there's no way to place buckets for every house, we return -1. First, we handle invalid inputs. If the string is empty or null, we return -1 since it's not a valid street. If there are no houses in the string, then no buckets are needed, and we return 0. Next, we address edge cases. For example, if there are adjacent houses with no empty space between them, it becomes impossible to place buckets, and we must return -1. Similarly, a single isolated house without any empty space nearby also makes the problem unsolvable. Finally, the core of the solution relies on a greedy approach, where we minimize the number of buckets by prioritizing placements to the right of each house whenever possible. Now, let's explore the greedy algorithm. We iterate through the string using an index, I. Whenever we encounter a house at street, I, we check if the immediate right side, street, I+1, is an empty space. If it is, we place a bucket there and skip the next index, as that space has been used. If the right side is not available, we then check the left side, street, I1. If the left side is empty, we place a bucket there. However, if neither side has an empty space, it means we cannot place a bucket for this house, and we return -1. While iterating, we also maintain a counter to track the total number of buckets placed. Once the iteration is complete, this counter gives us the result. This approach ensures that we minimize bucket placements while covering every house, provided it is possible. Additionally, we use early checks to identify unsolvable scenarios, saving computation time. This algorithm is efficient in both time and space. By iterating through the string from left to right, we ensure that every house is considered exactly once, making the time complexity O(n), where n is the length of the string. Since we don't rely on any additional data structures, the space complexity is O(1), which keeps the solution lightweight. The only extra variable we use is a simple integer counter to track the number of buckets placed. In terms of implementation, the code achieves the solution in a straightforward manner. We traverse the string, check conditions for each house, and either place a bucket or return -1 if placement is impossible. This simplicity makes the algorithm not only efficient but also easy to understand and debug. Let's walk through a concrete example to see the algorithm in action. Consider the input street equals h.h. Starting at index 0, we find a house and place a bucket at index 1, the empty space to its right, bringing the bucket count to 1. We then skip index 1 since it's already occupied by a bucket and move to index 2. At index 3, we encounter another house and place a bucket at index 4, again prioritizing the right side. the bucket count increases to 2. We skip index 4 and move to index 5. There, we find the last house and place a bucket at index 6, the empty space to its right, bringing the total bucket count to 3. After finishing the iteration, we return the result, which is 3 buckets for this street. The output for the example is 3 buckets, as we successfully placed buckets to cover all houses. Now let's examine a few edge cases. For the input h.h, only 1 bucket is needed, which can be placed at index 1. For hh, it's impossible to place a bucket since there's no empty space available, so the output is -1. For.h, the bucket can be placed either at index 0 or index 2, and the output is 1. These cases highlight how the algorithm handles a variety of scenarios, ensuring both correctness and efficiency. By accounting for constraints and edge cases, the solution robustly determines the minimum number of buckets or identifies when placement is impossible. This solution approaches the problem by iterating through the given street string and strategically placing buckets to minimize their count. The key is to ensure that every house, H, has access to at least one adjacent bucket, which can only be placed on empty spaces. 1. Initialization. The variable n is initialized to the length of the street string, and buckets is set to 0 to count the total buckets used. The I pointer is initialized at 0 to traverse the string. 2. Main loop. The loop iterates through the string until the end. If the current character is a house, H, we need to check for adjacent empty spaces. If the house is at the beginning or end of the string, and no adjacent empty space exists, it is impossible to place a bucket. The function immediately returns -1. 3. Placing buckets. If there's an empty space, to the right of the house, a bucket is placed there. The buckets count as increment, and the pointer skips the next house, if any, since it's already covered. Otherwise, if there's an empty space to the left, a bucket is placed there, and the buckets count as increment. For skipping and continuing, the pointer I is increment to continue checking the next character in the string. 5. Final result. If all houses are covered and the loop completes, the total bucket count is returned. If any house remains uncovered, the function would have already exited with -1. This solution ensures correctness and efficiency with an O(n) time complexity, as each character in the string is processed at most once. It handles edge cases, such as houses with no adjacent empty spaces, and minimizes the number of buckets used by prioritizing placement to the right of houses where possible. This is the Java implementation of LeetCode problem number 2086, minimum number of buckets required to collect rainwater from houses. The logic mirrors the provided Python solution, with adjustments for Java syntax and structure. The minimum buckets method iterates through the input string, determining the minimum number of buckets needed to cover all houses, H. Key differences include the use of Java methods like char at 4-character access and explicit type declarations for variables. The algorithm runs in O(n) time, as it processes the input string in a single pass. Here, we start by examining the street string h.h, which has 3 positions. The initial setup includes setting n to 3, representing the length of the street, buckets to 0 since no buckets have been placed yet, and I to 0 to begin scanning the string from the first position. At I equals 0, the character is H, indicating a house. Since a house requires an adjacent bucket, we check both sides for empty spaces. The left side is out of bounds, but the right side, at I plus 1 equals 1, is an empty space. So, we place a bucket there, increasing the bucket count to 1, and skip to I equals 2 to avoid overlapping coverage. Now at I equals 2, we encounter another house. This time, the left side at I1 equals 1 is an empty space. We place a bucket there, incrementing the bucket count to 2, and move to the end of the string. With all houses covered, we stop execution here. For the first example, the final state shows that we placed a total of 2 buckets to cover all the houses in the street. The output for this example is therefore 2. Now, let's consider a second example where the street string is .hh. The initial setup includes n equals 5, buckets equals 0, and I equals 0. Starting at I equals 0, the character is an empty space, so we skip to I equals 1. At I equals 1, we encounter a house. Checking for adjacent empty spaces, the left side at I1 equals 0 is empty. We place a bucket there, increasing the bucket count to 1, and move to I equals 2. Next, at I equals 2, the character is an empty space, so we skip to I equals 3. At I equals 3, we find another house. Checking its adjacent spaces, the right side at I plus 1 equals 4 is empty. We place a bucket there, bringing the bucket count to 2. After placing the bucket at I equals 4, we skip to I equals 5, which is the end of the string. For this example, the final state demonstrates that we placed a total of 2 buckets to ensure all houses are covered. The output for this example is 2. Now, let's analyze a third example with the street string HH. Here, the initial setup includes n equals 4, buckets equals 0, and I equals 0. We begin by examining the first position, where street, I, equals h. Since this is a house, we check for adjacent empty spaces. On the right side, at I plus 1 equals 1, we find an empty space. A bucket is placed there, increasing the bucket count to 1, and we skip to I equals 2 to avoid redundant coverage. At I equals 2, we encounter an empty space, so we skip ahead to I equals 3. Here, we find another house. Checking its adjacent spaces, the left side at I1 equals 2 is an empty space. We place a bucket there, incrementing the bucket count to 2. At this point, we move to I equals 4, which is beyond the end of the string. With all houses covered, the final state indicates that 2 buckets were placed. The output for this example is 2. From these examples, we can draw several key observations. First, a house, represented by H, must have at least one adjacent empty space for a bucket. When a house has an empty space on the right, it's optimal to place the bucket there to potentially skip the next house. If no empty space is available on either side of a house, it's impossible to collect rainwater, and the output should be -1. This approach ensures the minimal number of buckets is used by scanning the street left to right and prioritizing right-side placements when possible. The algorithm processes each character in the street exactly once, resulting in a time complexity of O(n), where n is the length of the street. Since it uses only a few variables to track the state, the space complexity is O(1). To analyze the time complexity of our solution, we start by observing that the input is a string, street, with a length of n. The algorithm uses a while loop to traverse through this string. In most cases, the pointer I moves one character at a time, but when a bucket is placed to the right of a house, the pointer increments by 2. In the worst case, the pointer progresses one character at a time, ensuring each position is visited exactly once. Within the loop, each operation, whether it's checking conditions, updating counters, or incrementing the pointer, takes constant time, or O(1). Since we process each character in the string exactly once, the total time complexity is directly proportional to the length of the string, resulting in O(n). The space complexity of the solution is determined by the resources used during execution. Here, the algorithm uses a few integer variables, such as n, buckets, and I, to keep track of the state. These variables require only constant space, or O(1). Additionally, no extra data structures like arrays or dictionaries are introduced, and the algorithm works directly on the input string without creating any copies. The memory used for the input string is external to the algorithm and doesn't count towards the additional space complexity. As a result, the space complexity remains constant, or O(1). Now let's consider the best, average, and worst-case scenarios for this algorithm. In the best case, if the input string contains no houses, denoted by H, the loop simply iterates through the string without placing any buckets or performing additional checks. Even here, the time complexity remains O(n). In the average case, regardless of how the houses and empty spaces are distributed, the algorithm still processes the string in O(n) time. While the number of conditions checked per iteration may vary, this does not change the overall asymptotic complexity. For the worst case, where every house requires checking both adjacent spaces, the algorithm still ensures each character is processed only once, maintaining a time complexity of O(n). By contrast, a brute force approach might try all possible bucket placements to verify coverage, leading to O(2 to the power of n) time complexity due to the exponential number of combinations to evaluate. Such naive methods would also consume more space, potentially requiring O(2 to the power of n) for intermediate storage. In comparison, the greedy solution is significantly more efficient, achieving linear time and constant space complexity. Finally, we can mathematically confirm the big O complexity of the algorithm. Since the loop processes each character in the input string exactly once, and each operation within the loop, such as checking conditions, updating counters, and moving the pointer, takes constant time, the total number of operations is proportional to the length of the string n. This confirms the time complexity is O, n. On the space side, the algorithm uses only a fixed number of variables, regardless of the size of the input, and no additional memory is allocated for data structures. This ensures that the space complexity remains constant, or O(1). Both of these metrics demonstrate the efficiency of our approach in solving the problem. When solving this problem, there are a few common mistakes to watch out for. First, placing buckets at every house may seem like a safe approach, but it's highly inefficient and leads to overestimating the number of buckets needed. Remember, a single bucket can often serve 2 adjacent houses, so it's crucial to optimize placement. Next, failing to handle edge cases can lead to incomplete solutions. For example, strings with consecutive houses like HHHH, or isolated houses like HH at the edges of the string, require special attention. Finally, mismanaging the placement order can also cause issues. Simply placing buckets from left to right without a strategy might leave some houses unserved or require extra buckets. Instead, focus on placing buckets in open spaces that can cover the most houses efficiently. Another common pitfall is incorrectly interpreting the constraints of the problem. For instance, configurations like HH with no dot spaces in between are unsolvable, and your solution must return -1 in such cases. It's vital to identify these scenarios early. Additionally, inefficient implementations, such as using nested loops or excessive condition checks, can significantly increase the time complexity, making the solution infeasible for large inputs. The optimal approach here is greedy, with a linear O(n) complexity achieved by iterating through the string just once. From an interview perspective, this problem is an excellent test of your ability to apply greedy algorithms. The key is to make local optimal choices, like placing buckets strategically, to achieve the global optimal solution. Also, recognizing this problem as interval-based can help structure your approach, as bucket placement decisions often depend on adjacent elements. During interviews, make sure to explain your thought process clearly, especially how you handle edge cases, and highlight that your solution runs in O(n) time complexity. This problem shares similarities with other LeetCode challenges, making it helpful to practice related problems. For example, LeetCode 55, Jump Game, requires making local decisions to achieve a global outcome, much like this bucket placement problem. LeetCode 122, Best Time to Buy and Sell Stock 2, demonstrates the greedy strategy in the context of stock trading. LeetCode 860, Lemonade Change, focuses on managing resources efficiently, and LeetCode 452, Minimum Number of Arrows to Burst Balloons, involves making optimal placement decisions in an interval-based scenario. These problems highlight how greedy algorithms can be applied in different contexts. While the greedy approach is the most efficient for this problem, it's important to understand the trade-offs of alternative methods. For instance, a brute force approach where you try all possible bucket placements can verify correctness for small examples, but it's highly inefficient for larger inputs. On the other hand, the greedy algorithm strikes a balance by providing an optimal solution in O(n) time, though it requires careful handling of edge cases to ensure correctness. An alternative worth considering is the two-pass solution. In this approach, you first use one pass to mark the locations where buckets are required and then perform a second pass to validate the placement. While this method may be slightly more complex to implement than the greedy approach, it offers a structured way to ensure correctness with fewer logical errors. This extra validation step can be particularly helpful in catching edge cases that might be missed in a single-pass approach. Overall, understanding the trade-offs between these methods can help you choose the most appropriate one based on the problem constraints and the context in which you're solving it, such as during an interview or in a competitive programming setting. That wraps up our discussion on LeetCode number 2086. We explored how to optimize bucket placement to collect rainwater while adhering to constraints. Remember, understanding problem constraints and edge cases is key to designing efficient solutions. Thank you for watching, and I hope you found this helpful. Don't forget to like and subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!